In the previous lecture, we were discussing direction fields. I hope you can listen me. Any issue? No, it's okay. Thank you. Yes, we were discussing direction fields. Let me remind you the main concepts. Direction fields. In fact, direction fields is a method for displaying general form of the solutions, the first order differential equations, graphically. We discussed lineal elements. Lineal elements are basically what they are: small line segments or maybe small arrows which define the slope at a certain point on the curve. Okay, how can we calculate the lineal elements? In fact, we can calculate the lineal elements without having the curve. If we have a differential equation dy by dx is equal to f of x y, and the domain is given, x belongs to some interval ab and y belongs to some interval ct. In fact, the domain is what? It's the product of Cartesian product of a, b, and cd. It's two-dimensional domain. So we divide this domain into a rectangular uniform grid. If this is your domain where the variables have all possible values, x and y, we define a rectangular grid. Means we divide this domain into equal points, okay, like this. And at each point, we compute the slope of what is the slope? Because dy by dx is a slope or gradient at any certain point. So this gradient is equal to this. So the gradient can be calculated if we have x and y, because this is f of x, y. So at each point, we find the gradient and we plot it, okay, just like this. In a, maybe it could be like this. So these are lineal elements having the same slope, which we compute using these functions. So these are the lineal elements. We discussed this last time. Once we have lineal elements, we can join the curves which passes through this point of the linear element, the middle point of the linear element. So we can draw infinite many curves by starting from different linear elements. And the curves which we plot, they follow the path along the linear element. So we can have infinite many lines, which gives us the one parameter family of solutions. Okay, and then we can compute the solution which we require, provided that the initial condition is given. For example, y at some initial value of x is equal to maybe some y naught. Okay, and the curve which passes through this point will be our particular solution. This was basically the story of direction fields. Now, another thing which I discussed is isocline. What is the isocline? Isocline is a straight line, which is the solution of that differential equation. What is a straight line? On a straight line, definitely the slope must be constant. Okay, if the slope is constant on these lineal elements, okay, if certain or maybe infinite many, there must be infinite many lineal elements, they might have constant slope. Then they will definitely give us a straight line. Okay, that straight line is basically called isocline. For example, if we have dy by dx is equal to maybe x plus y, then with the domain maybe minus 5, 5 cross minus 5, 5. Okay, this is the domain, or whatever the domain is. Then then you can see that at whenever we have x plus y, so we should have x plus y is equal to some constant value, maybe this constant is 0. Then from here, y is what? What is y is minus x. So y is equal to minus x is a straight line, which is this line. Okay. So at this line, every lineal elements, it will have slope 0. Okay. It will have slope 0 because we have chosen this constant to be equal to 0. So at this, all these points, all these lineal elements, they will have 0 slope. Okay. So if we draw a line passing through the points, the middle points of the lineal elements, then this line will form an isocline. In fact, isoclines in the solution of a differential equation, they divide the two-dimensional planes. Okay. If we have one isocline, then it will divide the solution planes into two subgroups. You can see that. Okay. The solutions in this portion of xy plane, they cannot cross this isocline, and solutions on this portion of the two-dimensional plane, they cannot cross this isocline and go to the other portion of this two-dimensional plane. Okay. In fact, isoclines, they divide the regions of the solutions of first order differential equation. Okay. Whatever the solutions curves are here, they cannot cross this isocline. They cannot come towards this portion of the xy plane. And the solution curves in this portion, they cannot go to the other portion. So they divide solution curves. We'll do this in an example later on. I hope you get it. If you have any question, you can ask me. If you have any question, you can ask me.
Okay, so like, how do we choose the value of the constant if it's supposed to divide the solutions?
Yes, good question. So how do we choose? We don't choose. There are infinite many. It could be 0, it could be 1, it could be 2, it could be 3, and so on. Okay, there might be infinite many isoclines in a solution of a first order differential equation. Okay, we do not choose. We see how many are there. You got it?
Okay, so yes.
Okay, you can see here the solution. Maybe let me show you. Let me share the screen here. This one. Look at the screen here. This is the isocline, and I have given an example in my notes. If you consider this ODE x plus y, this is the single isocline, but there will be infinite many isoclines. You can see this one in, I hope you can see it. Can you see this graph? Okay.
Yes.
Now you can see that here, in this example, they have plotted isoclines for many constants. They have chosen c is equal to 0, -1, 1, 2, 3, -2, -3, and there will be infinite many like this. Okay, so these are all isoclines. They all divide the solution into parts. No solution between these lines can cross these lines. Okay? You can see the lineal elements on the next page. So these are the lineal elements, some of the lineal elements. And then in the picture below, you can see some dense lineal elements. They have chosen more. Why is this mute on? Can you listen me?
Yes, there we can.
Okay. Now, if you see the picture below here, you can see the lineal elements, their pattern. Now, you can see here the solution curves. Okay. You can see the constants here. These are some of the solution curves which follow the pattern of the lineal elements. This is how we plot the solutions.
Sir, aren't the solution curves then crossing the lines?
Hmm?
Aren't the solution curves then crossing the EZ lines?
No, this is this the same example? I'm not sure because the lineal elements are not plotted for the constant values. Yes, they are crossing. Isoclines. Oh, I'm sorry. Isoclines, solution can cross isoclines, but not the singular points, the lines which represent the singular points. Yes. Sorry, I forgot it. Isoclines, the solution can cross isoclines, but not the singular points. Okay. I'm sorry for that. I forgot it. We'll discuss singular points of autonomous differential equations, and the solution cannot cross this, the isoclines, which represents the singular points, which comes from the singular points of the differential equation of the right-hand side function. So that's true. This is an isocline, but this isocline doesn't come up from the singular points of this right-hand side function. There is a difference. If the isocline is normal, it doesn't come from the singular points of the first order differential equation, then the solution can cross those isoclines. But if the isocline comes from the singular points of autonomous differential equation, we'll discuss autonomous differential equation after this, and then I shall give you an example that the isoclines which come from the singular points of a differential equation, they divide, in fact, the plane into different regions where the solution curves cannot cross those lines. So I'm sorry. You got it? Who was asking this question?
Yes, sir.
Okay, we'll discuss this thing later on after this, when we shall discuss autonomous differential equation. Okay, these are simple isoclines. There's a difference between simple isoclines and isoclines which comes from the singular points of the differential equation. Okay, now in this picture you can see that sorry. In this picture you can see that they have plotted all three things. They have plotted isoclines, they have plotted direction field arrows, they have plotted the sum of the solution curves. Okay, so the solution curves are crossing isoclines. These are simple isoclines. That's possible. Thank you for the question. Okay, next thing which we are going to discuss is autonomous first order differential equations. I'm going to stop sharing this thing and let's come back to the board. So there could be infinite many isoclines here. Okay. Now, autonomous differential equations autonomous first order ODEs. The differential equations of the form f of y, where the right hand side function f of y, this is function of y only, function of y only. The independent variable is not involved in the right hand side function explicitly. Okay, they are hidden. Of course, y is a function of x. X is hidden within y, but explicitly this right hand side function is a function of y only. Then we call this kind of differential equation autonomous differential equation. For example, dy by dx is equal to maybe y times 1 minus y. Another example could be dy by dx is equal to 1 minus y squared. These are two autonomous differential equations, first order. But if we write dy by dx is equal to the example which I gave you previously, this is not autonomous, okay? Why? Because x, the independent variable, appears here explicitly. But whereas in these examples, we don't have x, we cannot see x, in fact. Okay, we can see only y on the right-hand side function. So these kind of differential equations are autonomous differential equations. Autonomous differential equations are very important in order to model the logistic growth of certain commodity. We'll discuss these things in modeling. So these are autonomous differential equations. Now we are going to discuss critical points of the first order differential equations. Critical points only exist for autonomous differential equations because the points where f of y is 0. Okay, f of y, if we put f of y is equal to 0, this will give us certain points of y, maybe a, b, c, so on. It depends on the type of the right-hand side function. So these points are critical points. We can also say them equilibrium points. Okay, equilibrium points or singular points, maybe. I don't know, we call them singular points. Let me check it. I don't remember it. Stationary point, not singular point, stationary points. We call them stationary points. In fact, you would have studied these things, singular points, critical points in the calculus 1 course as well. If we put it equal to 0 and we find the values of y, in fact, you are putting dy by dx equal to 0. Okay, it's a first derivative. If you put first derivative equal to 0, then the values of x you find, those are critical points. In calculus 1, you must have studied these things. So these critical points, they give us also isoclines. Y is equal to a, some value a could be any real number, 2, 3, 5, anything. So these are all also isoclines. So these isoclines, they divide the plane into parts, into portions. And the solution curves, which of that first order differential equation, they cannot cross these isoclines. This was what I was talking about when I told you earlier that the solution curves cannot cross isoclines. But the isoclines which comes from the critical points or the stationary points of that first order differential equation. These are not normal isoclines. Okay? In fact, we put it equal to 0. But normally, what is the definition of isocline? Its definition that the right hand side this is equal to constant. But not all constants are 0. So not all critical points are also, so if we put it equal to 0, then there are special kind of isoclines. Okay, if we put it equal to constant, then those points are not critical points. Let's discuss this thing. For example, this thing. Okay, divide by dx. Consider that this differential equation divided by dx is equal to 2y 3 minus y. Okay, find the critical points of this differential equation. What are the critical points? They are straightforward. We put the right hand side function y is equal to 3 minus y equal to 0. So the critical points are y is equal to 0 and y is equal to 3. So these are also isoclines. Okay, these are isoclines. Now these isoclines will divide the two-dimensional plane into 3 regions. Okay, the one is y is equal to 0, which is x-axis. This is your x-axis, this is your y-axis, and the other one is y is equal to 3, maybe 1, 2, 3. So this straight line, horizontal line, is an isocline. Okay, this is y is equal to 3. Now, these isoclines have divided the two-dimensional region into two-dimensional plane into 3 regions. How many? This is the first region. Okay, this is the region 1. Okay, this is the region 2. And this is the region 3. Now, there are 3 kind of solution curves. The solution curves within this region, they will remain in this region. They cannot go to the other regions. Solution curves in this region, they cannot go to this or this region. Similarly, this one cannot go there. So these isoclines, they in fact divide the xy plane into certain regions. Okay, I hope you get it now. The next is phase portrait. What is the phase portrait of autonomous differential equations? Phase portrait is the portrait which tells us the behavior of the solutions in all regions of xy plane. If we have this differential equation, we know its critical points. We divided the xy plane into regions, whatever the number of regions we get. Now we'll see the behavior of the solution curves in all these 3 regions. So how can we compute the behavior? These are the isoclines. Now we divide the y-axis into 3 regions. For example, the first region is what? It is from negative infinity y to 0. This is your first region, sorry, third region. The second region is between 0 and 3, because this is 0 and this is 3. So second region is between 0 and 3. And the third region is y is greater than 3. Okay, or you can say y is greater than 3, less than infinity. Now you check the sign of that function, f of y, in these 3 regions. Okay, you choose any one value here, you put it in y, f of y. For example, you choose -1. If you put -1 here, you'll get positive here, you get negative here. So f of y will be negative here. In the second region, you choose any one value. You choose 1, maybe. You get positive here, you get positive here. So here, the behavior of the solution is positive. Means the slope or the gradient is increasing. In a third region, you choose any value. You choose 4, you get negative here, you get positive here. So you get negative here. So the slopes of the solution curves in this region will be negative. Slope of the solution curves in this region will be positive. Here, negative. So if you don't mention this thing, okay. Now, what is phase portrait? Phase portrait is this thing. You draw the critical points here. On the y-axis, sorry, this one. And then you draw the arrows according to these things. यहाँ पे 0 से 3 तक. From 0 to 3, we have a positive slope. So the solution must be increasing here. Solution curves. They have positive gradient here. In this region, we have negative gradients. In this region, we have negative gradients. So this is the phase portrait of this differential equation. Now, if we combine the previous and this picture, we can have this thing, this thing. Okay, so this is y is equal to 0, and this is y is equal to 3. Now you have a lot of information about the solution curves of this differential equation. Okay. Now, if you are given the domain, for example, maybe -3 to 3 cross -3 to 3. Okay. यहाँ पे 1, 2, 3, 1. Sorry. यहाँ पे नहीं. We don't draw it here. We draw it here. 1, -1, -2, -3. Really 1, 2, 3, 1, 2, 3. यहाँ पे 1, 2, and 3, and similarly 1, 2, and 3, whatever. Okay, you have in order to see the solution here, you have to take it bigger. यहाँ पे आप -10 से 10 ले लें, or whatever. You just take R square, maybe. Now you divide the given domain into a rectangular grid, and then you plot the lineal elements, and then you can draw the solution curves. Okay, you just look at the board. Sorry, the students are sitting here in the classroom as well. So look at there in the notes. It will save some of my time so that I can show you. Sorry. So I have done all this thing here and then here. So these are the solution curves after plotting the lineal elements. I hope you can see it. So you can see that in the middle region, the solution curves are increasing. In the two other regions, the solution curves are decreasing. Okay, and no curve has crossed these isoclines. These are the direction fields of this example, which I have written on the board. Sorry. Now the question is, which curve is our solution? The solution which we required, which is valid for our situation, okay, our physical phenomena. For that, we need to have an initial condition. I told you, in order to get a particular solution, you must have initial condition. If you have an initial condition, for example, y at maybe 0 is equal to 1. Okay. Then the solution curve passing through x equal to 0 and y is equal to 1. This solution curve, which might be kind of this thing, okay, according to that that picture of direction fields, this will be our solution curve, which will be required in our physical situation or in our project. This is the only solution which we require. If this initial condition, if I change it, y at 4 is equal to maybe 5 or something like that. So this is what? This is x equal to 4 and y is equal to 5. Okay. You choose here x equal to 4 and y is equal to somewhere here 5. Then the solution curve passing through this point will be our solution, this one. We won't have this as a solution. If the initial condition is y at 0 is equal to 5 or maybe whatever, 4, then here we have 3, 4, 5. Then the solution curve passing through this point will be our solution. Only a single curve will be our solution. Otherwise, we have infinite many solution curves here, as you can see in the figure of direction field of this question in my notes. There will be infinite many solution curves, and these curves are basically jam-packed with each other. And here the solution curves are decreasing. So it is like this. So this was all about the direction fields. If you have any question, you can ask me. The direction field is a method which gives us the solution graphically, okay? The general form of the solution graphically. If we are unable to solve a certain differential equation, then we can have an idea of the solution, general form of the solution by plotting it. Okay, it's direction fields. That we can do it easily because the right-hand side function is a function of x, y. In case of autonomous differential equation, it's a function of y only. But autonomous differential equations are more important. They have a lot of applications in daily life problems. For example, logistic models, growth of populations, and growth of certain bacteria in a lab. We'll discuss these applications after discussing these things. If you have any question, you can ask. Okay, let me stop sharing it and go to the other board. Now, autonomous differential equation can be solved by using the techniques which we have already discussed. For example, the autonomous differential equation which I have written there on the previous board, it is what? It is dy by dx equal to 2y into 3 minus y. Okay, these differential equation can be solved. Dy by dx is equal to, it was 2y 3 minus y. How can we solve it? Anyone?
It's a separable equation.
It's separable differential equation. Separable first order differential equation. We can separate the variables and we can integrate and get the answer. You can plot, once you get the solution, you can plot that solution. If you plot that solution should be similar to the solution curve which we obtained by using direction fields. Okay, you can cross check. I hope you can do it yourself. If you have any difficulty, you can ask me. So this was all about direction fields. There are more examples given at the end of my notes and of course in the book. You can try those exercises while practice. I have given a lot of exercises here. You can see them. The next thing which we are going to discuss is the modeling using first order differential equations, which is, I hope you will enjoy by looking at the applications of differential equations. So modeling with first order ODEs. The first model which we look at of the first order differential equation, which can be used in daily life applications, is the population growth model. Okay. First model is population growth model. Any kind of population which is growing only, okay? There's no decay. We assume that in this first particular model, which is very obvious model. In this model, we assume that a certain population of bacteria, maybe a certain biological organism, it's growing in a certain container or in a certain thing. Okay. They are only growing. There's no death. We are not considering death of the bacteria at initial state now, right now. We'll discuss later on the more possibilities. Will enhance, will expand the model by incorporating deaths of the bacteria or any other thing. For example, you can take the population of Lahore, maybe, or Pakistan. Okay, you can model it. But first thing, we are assuming that people are not dying. Okay. In that case, we say that the rate of change of population of a certain thing is what it is proportional to the current population. Okay, this is the very basic population growth model. Okay, when we say that the rate of change of the population is increasing, which is proportional to the current population. If we have less number of population initially, then the growth will definitely, it will be proportional to that population. If the population is large, then the population grow accordingly. Okay. So if we remove the sign of this proportionality, we can have some constant of proportionality and P. Okay. And it depends on the initial population as well. Initial population is what? P population at time 0. It should be, or it could be P naught. P naught is some constant. So this is your complete population growth model, where we have assumed that the population is only growing. It's called birth process or whatever. Let me check it. What is the pure birth process? It's called pure birth process. Okay, it contains only birth process. Only the population is growing. Now, if we say that in this case, k must be greater than 0. Okay, in a pure birth process, k should be greater than 0. Okay, if we say that dp over dt is proportional to some lambda times p, where lambda is less than 0, where population at time 0 is p naught, then this is what? It is pure death process. Pure death process. Because the people are dying only. We are not considering the birth of the new people. Okay? So this is called pure death process. If we combine these two things, then we can incorporate birth as well as death process. And that model would be dP by dt. It is proportional to both, okay, birth as well as death. So that model will be K minus lambda times P, where as the initial population is some constant number. Now this model will give us both birth as well as death process. But one thing which is important to mention here is that it depends now which one is greater. If K is greater, then the population is, if K is greater than lambda, then, or you can say that if K minus lambda is greater than 0, then the population is growing. If K minus lambda is less than 0, then the population is decaying. Okay, so this model is also called decay models, population decay models. Okay, decay model. That was population growth model, and that was population decay model, and this is the combination of these two models, which can incorporate birth as well as death. We can add other factors as well. For example, a pandemic can affect the death rate. Okay, that can affect. We can add some other factors here which can contribute to this model and gives us birth, death, as well as certain kind of effect of pandemic. जैसे कोरोना है या कोई और पैंडेमिक है, उससे आपके मॉडल पे या पॉपुलेशन के ग्रोथ या डिके पे डेफिनेटली इफेक्ट पड़ेगा. But these are basic models. We'll discuss more complex models later on. Okay. Now, let's do an example of this thing. And then we should move forward. Now, which one? It's very easy. These are very easy examples. A population of a small town grows proportion to its current population. That's an example. Example. I'm going to read it. You just listen it and you can see in my notes. A population of a small town grows proportion to its current population. The initial population is 5,000. We assume that initial population is 5,000. Let's define it in this way. Initial population is 5,000. Okay. And it grows at a rate of 4% per year. Okay. Growth rate is what? It is 4% per year. Okay. Find an ODE to model the population growth, determine the population after 5 years. Okay, we need to compute population after 5 years. And another question is determine how long will it take the population to double. Okay, kitna time lagega ye population double hoga. Okay, after 5 years and then double. So the population growth model, we know it is dP. First of all, you define the variables. In modeling, the first step is you define the variables. Okay, define the variables in order to convert or transform this problem into a mathematical model. Okay, the first step is you define variables. Yahan pe define variables. Okay. Now it's a population. We know that we are going to model a population growth. Population growth can involve time because it grows with the passage of time, and we need a population a variable to describe the population as well. For example, we say that P of T represents what? Population at certain time T, at any time T. So, okay, let P denotes, you can say that. Let this denotes population at time T in years. Okay. So this is your P is your population variable, T is your time variable in years. Okay. Then the rate of change of population is what? dP by dt is equal to K times P, because there is no death rate. People are not dying, only the people are growing. Okay. There's no death process. So this model will be sufficient. K should be greater than 0, because what is the K here? Is the rate of growing, rate of growth. What is the rate of growth? It is 4%. So K should be what? 0.04. And what is the initial population? Initial population is 5,000. So P at 0 is 5,000. Okay. Now, what to compute now? Okay. Next thing is what to compute. We define variables. We define here the model, the appropriate model. Okay. First of all, we define the variables, and then we define the model, and then we define the initial condition as well. You have to define the initial condition if you have it. If you don't have, we'll see what we do if you don't have. But you should have initial condition. Otherwise, you can't solve it completely. What to compute? Population after 5 years. Means population at 5, and when the population is double. Okay, when the time, we need to compute the time when the population will be double. The first thing which we need to compute here, and the second is the time when population will become double. Double means double of what? Double of initial. So it should be 10,000. We need to compute P of T is equal to 10. We have P of T is equal to 10,000, and we have to compute T. Okay, this thing. So this is all the information we are given in the model, and what would be the appropriate model we are going to use, and what we have to compute. So you have to analyze your situation first. You have to define the variables. You have to choose the appropriate model, and then you have to decide what to compute. This is all the information given in the question. Now let's attack it. Let's try to solve it. Now, this is our model. dP by dt is equal to 0.04 times P. It's a very simple separable differential equation. You can solve it easily. dP by dt is equal to 0.04 times P. So you can take it 1 by P, dP is equal to 0.04 dt. Okay, so this will be natural log of P, and this will be 0.04 T plus C, where C is the constant of integration. Now, if we have a log P here, then we can have P is equal to what? Exponential of 0.04 T plus C. Okay, so this is what? This is your P of T, and this is e raised power 0.04 T times e raised power C. And we can write it further in the form P of T is equal to some kind of constant A times e raised power 0.04 t. So this is your solution. I hope you can see it. Now you can see the growth is exponential. Okay, this is exponential growth in the solution. When the time passes, when t is 0, we have initial condition A. So A is what? This is your initial population. Okay, why? We can use initial condition here in order to get the value of A. A is unknown constant. A is constant of integration. Okay. A is constant of integration. By using P at 0 is equal to 5,000. It was given. So what we get here, 5,000 is equal to A times e raised power 0. So what do we get here? A is 5,000. This thing. Now the complete solution, which is the particular solution. Now you can see that this is your particular solution. I told you the particular solution is a solution which is obtained by from the general solution by using the initial condition. Okay, so this solution is, in fact, it suits your situation. Okay, 5,000 times e raised power 0.04 times t. So this is your solution. Once we have a solution, we can compute population after 5 years, 10 years, 100 years. Okay? We just have to put t is equal to that thing. So what we had to compute population after 5 years. Okay, the population after 5 years would be what? You just put t is equal to 5 here. The first thing, the answer of first thing, p of 5 is equal to 5,000 e raised power 0.04 times 5. Okay, you solve it and you'll get the solution. What is the solution? It's 6,107 approximately. It's not, because this will come in decimals, fractions. So 6,107 approximately after 5 years, if this is the growth rate, 4%. Now we need to compute the time when the population doubles. The second thing, can I erase it? If you have, everything is written in my notes. You don't have to note down it. Just you can note down important points. Otherwise, everything is written. The second thing, population, when the population doubles. What does it mean? We need to compute time when the population doubles. Okay, as p of t is what? It is 5,000 times e raised power 0.04 t. Okay. Now the p of t is given. P of t is what? It is 10,000 equal to 5,000 e raised power 0.04 t. T remains t because we have to compute t. Okay. Now from this equation, we have a single unknown. We can compute t. So always 5,000 will give us 2 equal to e raised power 0.4 t. This will always be 2. Okay, because here we have initial, here we have double of that thing. Okay, double, if यहाँ पे अगर double होगा तो definitely ये 2 यहाँ पे आएगा. यहाँ पे natural log of 2, 0.04 t, natural log of e. You take log on both sides. This natural log of e is equal to 1. So what is t? T is natural log of 2 divided by 0.04. Okay. So this is called, so this is your time when the population doubles. And what is this time? It is 17.328 years. Okay, the value of this thing is 17.328 years. Okay, the population of that town will be double after 17 years. If the same growth rate applies, nobody dies. Okay, this is called doubling time. This is called doubling time. Natural log of 2 will always come here. And what is this? It is the growth rate. Okay, so this is fixed. Doubling time. This is called doubling time, and the doubling time is some t is equal to natural log of 2 divided by the rate, growth rate. This is your doubling time of the population when there are only pure birth process. If you have any question, you can ask me. Similarly, you can have half time or half life, half time. When the population remains half of the original population in the pure death process. Okay, you can see these things in my notes. I hope you can understand. Okay, population growth जो pure birth process होते हैं उसमें doubling time होगा और जो pure death process होंगे उसमें half time होगा या half life आगे चल के. We'll apply these models on certain substances as well. For example, radioactive material. If you have uranium that is basically, there is a decaying process all the time on the certain kind of materials. Okay, for example, uranium, polonium, just atom bomb नहीं बनता जिससे. The atoms of those material, they release atomic fragments. Okay, and they always decay with the passage of time. We can also apply these models on the decay of certain processes, certain materials, and that we call a radioactive decay. Okay, pure death process model can be used for the radioactive decay as well. We'll discuss after this. This model, population growth model, this one, or this one, or we'll discuss more models. Mathematical models, they can be used in different situations for the different models as well, okay? For the different physical phenomena. जैसे कि ये मॉडल है, ये पॉपुलेशन ग्रोथ मॉडल है या ये डिके मॉडल है, ये सिर्फ पॉपुलेशन के लिए यूज नहीं होता. It can be used for radioactive decay of substances of certain material as well. ठीक है, तो एक मैथमेटिकल मॉडल ये नहीं है, जरूरी नहीं है कि वो किसी एक फिजिकल फिनोमेना के लिए ट्रू हो. That can be true for the multiple physical phenomena. ठीक है, let's discuss radioactive decay now, and then we'll move forward. अच्छा, इसमें there must be some example there. In certain examples, we are not given the growth rate. We are only given the population after a certain time, or we are given some other condition which help us to compute the growth rate. For example, यहाँ पे जो second example है इसकी, यहाँ पे एक और एग्जाम्पल भी है, पेज नंबर 9 पे है शायद, हाँ, मॉडलिंग का जो नोट्स है ये देख लें. इसमें birth as well as death rates दोनों given है. So we have to incorporate death rate as well in the model. A culture of bacteria grows proportion to its current population. If the bacteria grows at a rate of 10% per hour and die at a rate of 5% per hour, what will be the population of bacteria in one day? ठीक है, आपके पास एक लैब में कंटेनर है जिसमें आप बैक्टीरिया को ग्रो कर रहे हो, उसमें सर्टेन बैक्टीरिया मर भी रहे हैं, 10% ग्रोथ रेट है, 5% डेथ रेट है, ठीक है, पर आवर के रेट से, ठीक है. So we have to compute what would be the population of bacteria after 24 hours, means one day. ठीक है, so I hope you can do it. क्योंकि डेथ रेट क्या है, लेस है as compared to birth rate, so it is a growth model. Okay, अगर डेथ रेट ज्यादा हो ग्रोथ रेट से तो इट इज व्हाट, पॉपुलेशन डिके मॉडल. ठीक है, ग्रोथ मॉडल में क्या होगा, हमेशा ग्रोथ होती रहेगी. हाँ, k minus lambda, k is 10% in 0.1 and the death rate is what, 5%, it is 0.05, the rest is same. ठीक है, I hope you can do it. Another example in the growth models is again, a culture of bacteria grows proportion to its current population. If the initial population of 500 bacteria increased by 15% in 8 hours, ठीक है, initial क्या है, population at 0 is 500, ठीक है, और after 8 hours जो है वो कितनी है, 15% इंक्रीज है. ठीक है, 15% increase after 8 hours. अब हमें ये इंफॉर्मेशन गिवन है, हमें इनिशियल कंडीशन गिवन है और हमें ये बताया गया है कि 8 घंटे के बाद वो 15% ज्यादा हो जाता है. वी आर नॉट गिवन रेट पर आवर, वी नीड रेट ऑफ ग्रोथ क्या है, दैट शुड बी पर आवर. अच्छा, हमने कंप्यूट क्या करना है यहाँ पे, what would be the population in one day. ठीक है, population at 24, ये कैलकुलेट करते हैं. ठीक है, अब हमें यहाँ पे रेट नहीं गिवन, अब रेट ऑफ ग्रोथ या डिके नहीं गिवन तो फिर कैसे कंप्यूट करेंगे. हमें इनिशियल पॉपुलेशन गिवन है, हमें ये गिवन है कि 8 घंटे बाद 15% इंक्रीज है, 1 घंटे बाद नहीं गिवन. हम क्या करेंगे, हम ग्रोथ रेट यहां से निकालेंगे, विल फाइंड इट फर्स्ट and then we solve more. I hope you can see and you can understand easily how to find the growth rate. It's not that much difficult. चलें थोड़ा सा आपको बता देता हूँ कैसे करना है इसको. Then that. But in practical situation, we look for a unique solution. We look for the solution which fits to our situation, our model. ठीक है, तो हमें हमेशा हमारी यही बेसिकली कोशिश होगी कि हमारे पास एक यूनिक सोल्यूशन आए जो कि परफेक्टली फिट हो हमारी सिचुएशन. वी आर नॉट लुकिंग फॉर मल्टीपल सॉल्यूशंस. ठीक है, इसलिए हम क्या करते हैं, वी मेक श्योर कि हमने जो मॉडल बनाया है दैट इज परफेक्ट, दैट सेटिस्फाई द assumptions or the properties of that theorem. ठीक है, then you can have a perfect solution. Otherwise your model is not, you can say that ill-posed model. ठीक है, that will give you maybe inaccurate solutions. You don't do that. So यहाँ पे हमारे पास P of 0 given है और P at 8 जो है वो क्या है, initial plus 15% of the initial population. ये होगा ना? So this will be your population after 8 hours. So it will be what? 500 plus 0.15 into 500. And this is what? 575, I think. Yes, 575. This is your P of 8. From P of 0, we can compute the initial, constant of integration. And from P of 8, we can compute the K. Because we don't have the value of K here now in this situation. So we know the solution, we know the model. The model is what? The model is dP by dt equal to K times P. Okay. And the solution is P of t is A times e raised power kt. ये होता ना? The solution is this. Now we have A is what? It is constant of integration. It should be equal to 500. We know it because when you put t is equal to 0, we'll get A is equal to 500. So this is your 500 e raised power kt. Now still the solution is incomplete. Now this second condition helps us to find the k. Now you can put it 575, 500 e raised power k into 8. Now what is the unknown here? The only unknown is k here. We can compute the value of k. Okay, I hope you can do it. So the value of k, you divide this thing over here, there. You take the log on both sides, and then you can compute the value of k. The value of k is what? 0.01747. It's 0.01747. Now, once you have k, you can put k back here, and you can answer any question asked in your situation, in your question. I hope you get it. If you have any question, you can ask me. You can plot these solutions. In fact, they are exponential solutions. Okay? They start with, for example, this solution will start from 500. Okay? And it will go up there. These are exponential kind of solutions. The previous जो हमने solutions find किए थे, वो भी क्या होंगे? Exponential growth model. इन सबको हम exponential growth model भी कहते हैं. क्यों? क्योंकि इनका solution जो है, that is an exponential function. और जो दूसरे हैं pure death process में, उनको exponential decay models. ठीक है? I hope you get it. If you have any question, you can ask me. Let's discuss very quickly and briefly radioactive decays. It uses the same kind of model. I hope you can do it yourself, but let me give you a brief introduction to those things. Radioactive decays. Radioactive decays, I have given an introduction here, who defined them, who introduced them. So in nature, certain kind of substances, they can spontaneously emit elementary particles. Okay? जैसे कि आपको मैंने बताया था, uranium है, polonium है, many other materials, they emit certain particles of nuclear fragments, you can say that. So the process of these spontaneous emit of particles, this process is in fact called radioactivity. ठीक है, आपने सुना होगा कि वो जो रेज radioactive materials जो हैं, they emit rays. Those rays are basically, they also contain certain atomic particles. ठीक है, in this process those substances they decay after certain time. अच्छा, यही मॉडल जो है आप बोन्स पे भी कर सकते हैं. ठीक है, ह्यूमन जो बोन्स हैं, ठीक है, वो भी क्या करती हैं, डिके करती हैं. ह्यूमन बॉडी तो बहुत जल्दी डिके करती है, वो भी डिके करती है. ठीक है, लेकिन बोन्स जो है, दैट इज सब्सटेंस दैट डिकेज विद अ सर्टेन पैसेज ऑफ टाइम. ठीक है, तो उस चीज को भी हम मॉडल कर सकते हैं, बट दैट टेक्स लॉट ऑफ टाइम. मतलब सदियां गुजर जाती हैं, तो आप किसी भी जानवर की या किसी भी मतलब उसकी हड्डियां जो हैं वो बहुत slowly decay होती हैं. So by computing the certain rate, we can say that after that much time, this skeleton will disappear. ठीक है, जैसे कि डायनासोर्स और उसके स्केलेटन अभी तक स्टोर हैं, उसको कैसे वो मतलब पता करते हैं कि ये कितना पुराना है. ठीक है, so these kind of models can be used to compute कि ये डायनासोर 1 billion years पुराना है, ऐसे ही कहते हैं ना. ठीक है, so those are decay models, but they are not very simple. We are discussing very basic kind of models. ठीक है, so the model is same. dn by dt is equal to lambda times n. Okay, where n of t is what? N of t represents decay of certain material or certain substance at any time t. Okay, when lambda is less than zero, because we are discussing decay or the pure death process. Okay, so these two models are similar. We have just changed the notation. We have done nothing else, but they are describing two different physical phenomena. One is population growth and the other is decay. Okay, so you can see the examples as well here. Radioactivity. Polonium-218 is a substance which decays exponentially. Okay. Polonium-218 is a substance which decays exponentially. The decay rate is 23.1 per minute. 23.1% per minute. मतलब आपने इतनी बड़ी स्लैब रखी पोलोनियम की, 1 मिनट उधर गए वापस आए तो 23% कम हो गया. ठीक है, मतलब आप 5 मिनट बाद आएंगे तो वो गायब हो जाएगा. ठीक है, सो यू हैव टू स्टोर इट एट अ सर्टेन मे बी प्लेस के वो डिके रेट उसका स्लो हो जाए. इसलिए आपने देखा होगा कि न्यूक्लियर प्लांट्स जो होते हैं वो नीचे कहीं जाके पता नहीं कहाँ पे, और बहुत ज्यादा ठंड होती है उनमें, सो दैट कि उसका जो डिके प्रोसेस है वो मतलब रुक जाए. उसको इतना टेम्परेचर या ऐसी सर्टेन सिचुएशन उसको चाहिए होती है, एनवायरनमेंट ऐसा चाहिए होता है कि उसमें उसका डिके ना हो. अदरवाइज तो आप पानी पीने जाएंगे तो पीछे आएंगे तो यूरेनियम खत्म हुआ हो. So that's the thing. Find an equation that satisfies the ODEs. This or easy. हाँ, हमने सबसे पहले question is this: the polonium-218 decays exponentially. The decay rate is this per minute and can be modeled by. Definitely, the model will be dp by dn कह दें, कुछ भी कह दें. dn by dt is equal to negative 0.231. Why we put negative here? Because the decay rate. Okay, you have to put a negative sign here. यहाँ पे n आ जाता, ठीक है. Find an equation. हो गई equation हमारे पास आ गई. अच्छा, क्वेश्चन दूसरा पार्ट क्या है? If 100 grams of polonium is present at t is equal to 0, means n at 0 is 100 grams. ठीक है, ये है. How much is it present after 90 seconds? वो कहते हैं ये पहले ही है, दूसरी क्या है? ये n 90 सेकेंड्स के बाद ये कितना होगा, और ये डिके रेट आप देखें पर मिनट है, तो 90 सेकेंड्स क्या होंगे? 1.5 here. You have to compute here n at 1.5. और तीसरा पार्ट क्या है? What is the half life of polonium 218? Half life. I told you what is half life. ठीक है, तो half life means, इसका मतलब क्या होगा कि आपका जो n है, n of t अगर इनिशियली कितना है 100 grams, initially it is 100 gram और exponential of negative 0.23 t, ये इसका सोल्यूशन होगा. हाफ लाइफ क्या होगा? यहां पे क्या पुट करना है? 50. ठीक है, so it should be 50 here, 100 times e raised to the negative 0.23 t. So after solving this, you can compute half life, and that will also be log of 2 divided by lambda. But the lambda is half of 2 नहीं होगा, half of minus हो जाएगा ना. देखिए अब जो हाफ टाइम होगा यहाँ पे, इंस्टेड ऑफ 2 you would have 1/2. ठीक है, यहाँ पे आपके पास हाफ लाइफ में log of 1/2 आ जाएगा, क्योंकि यहाँ पे आप जब इसको डिवाइड करेंगे यहाँ पे तो 1/2 आ जाएगा ना. यहाँ पे फिर दो बोथ साइड्स पे आप log लेंगे, you get this thing. So this is your half life. ठीक है, log of 1/2 is negative, or you can say that this is equal to log of 1 minus log of 2 divided by k. Log 1 क्या होगा? 0, and this is equal to negative log of 2 by k. This is your half life. ठीक है, मतलब इतने टाइम के बाद वो सब्सटेंस आधा रह जाएगा. अच्छा, जो डिके मॉडल्स हैं, एक्सपोनेंशियल डिके मॉडल्स हैं, उनका जो ग्राफ होगा, दैट इज द एक्सपोनेंशियली, दैट विल डेफिनेटली एक्सपोनेंशियली डिके. ओके, तो आपका जो मॉडल ग्रोथ मॉडल्स हैं उसमें दिस विल बी योर काइंड ऑफ सॉल्यूशन ग्राफिकली, बट हियर द सॉल्यूशन आपके पास जो डिके होगा वो अगर 500 से स्टार्ट हो रहा है तो वो डिके मॉडल ऐसे सॉल्यूशन होगा. ठीक है, सो दिस विल बी योर एक्सपोनेंशियल डिके मॉडल. ग्रोथ मॉडल्स में ग्रोथ जो है वो अप टू इंफिनिटी है, और डिके मॉडल्स में जो डिके है अप टू 0 है. डेफिनेटली जो पोलोनियम होगा आफ्टर सर्टेन टाइम इट विल वेनिश, तो 0 आ जाएगा ना आपका सॉल्यूशन. सो दैट इज टेक्निकली करेक्ट, दैट द सॉल्यूशन इज गोइंग टुवर्ड्स 0. ठीक है, I hope you get it. If you have any question, you can ask. If you don't have any question, we can stop today here.